Hey guys, today I'm going to take you through how to solve for intersections of lines in both 2-space and 3-space. So firstly, let's take a look at intersections of lines in 2-space. So we're familiar with this back from our studies in grade 10 when we solved linear systems with substitution and elimination. So we know that two lines that are on the same flat Cartesian plane can intersect in one point, as we can see from the graph here. They can also have infinite intersection points if they are what we call parallel and coincident, meaning they're essentially the same line. And they could also have no points of intersection. And this happens when the lines are what we call parallel and distinct. So they have the same slope, but they're not the same line. So if it's a regular linear system expressed in, let's say, y equals mx plus b form, or in scalar form or standard form, we can solve these as we usually would from our previous studies using substitution or elimination. Now we'll do something similar if we have a line in 2-space expressed with our new vector type notation. But we might have to do a little bit of extra work to kind of get this set up in order to do elimination. So what we're going to do is we're going to take something in vector form and we're going to write the parametric equations of each line. Then you'll have an x and a y for each line. You're going to set the x's equal and the y's equal and simplify each resulting equation. So you should have two equations after this. Now you're going to solve for your parameters. Typically they'll be s or t, but if there's something else, solve for one of them using elimination. You're going to take that answer that you got from step 3 and plug it back into the parametric equation of the line with the parameter you just solved to find the xy coordinates. Now we can also solve for the other parameter that we didn't solve for and sub that back in to check our answer. That's not a necessity, but it is a great way just to make us feel a little bit more confident that we solved for the correct point of intersection. So let's take a look at an example of two lines in vector equation format. So as I said, we're going to take both of our lines and we're going to set them up in parametric form. So for our first one, I'm going to take the x components and separate them out from the y components. And then same thing for our second one. Okay, and now if I'm trying to solve for where the lines intersect, that is the point where x and y are both equal. So if I'm trying to solve for the point of intersection, that means I can set the y's equal to one another and the x's equal to one another. So if x equals this and x also equals this, and I want to know where they're equal, they have the same x coordinate, I'm just going to set those two pieces equal to one another. And we're going to simplify out this equation a little bit by moving, you can move everything to one side or you can move the constants to one side and the variables to the other. So I might just do that. We'll have 5 equals, let's go 3t minus 3s. So this is going to be my first equation. And I'm going to do the same thing with the y's. So I'm going to set if y is equal to this, and also this, I'm going to set those equal to one another. And we'll move the constants to one side and the variables, or the things with the variables, to the other. Okay, perfect. So that's going to be my second equation. So we need to choose if we want to eliminate the s's or the t's. So you can really choose either of them. I think maybe we'll do equation 1 times 2 and equation 2 times 3 to get our new equations here. And I'm making the s's equivalent in this case. Okay, then you need to decide whether we're adding these equations or subtracting them. So I have a negative 6s and a positive 6s. So if I add them, the s's will cancel. So we've got 28 equals 21t. And when we divide out here, we'll get 28 over 21, which reduces to 4 over 3. So now that we know we have t is equal to 4 over 3, I should be able to actually sub this back into my parametric equations for L2. Now I chose L2 because L2 has the parametric equations in terms of the parameter t. If you had solved for S, you would be plugging back into line number 1. So we're going to sub this back in for L2. Just going to zoom out a little bit here so I can see them. All right, so here the 3's cancel and we're left with x equals 2, and then we'll do the y's. Okay, this one, ideally we'd like to keep in exact form if possible. So we'll have 20 over 3, and then I guess we can just switch this 2 to 6 over 3. So that will leave us with 14 over 3 for our y. Okay, so that means that the lines do intersect, and we have a point of intersection at the point 2, 14 over 3. Now, what you might find if your lines actually don't intersect are a couple different things. It depends on whether they're parallel distinct or parallel coincident. So what ends up happening typically at this step right here when you solve for your parameter is either you will get an always true statement or a never true statement. And what I mean by that is a lot of times when our lines are, well, not a lot of times, but when our lines are parallel and distinct and they have no points of intersection, oftentimes what we'll end up getting is kind of a statement that doesn't make sense. So we'll get something like 8 equals 0t, right? So when we solve, it just so happens that the s's cancel out and the t's cancel out, and I end up with something like this. Now, we of course know that there's no value that can be plugged in for t here that will allow this to be true. So if you get something like this at this point right here, you can stop and you can say these lines do not have a point of intersection and they're parallel distinct. Now, what you might also get is something like this. 0t equals 0, and this is true for any t actually. So this means that the lines are parallel coincident if you get an always true statement, and that means that you have infinite points of intersection. So just look out for those possibilities. We're going to take a look at some of these possibilities in 3D when we move on to our next examples here. Okay, so we're going to take a look at some possibilities for intersections of lines in 3 space. Now this can kind of be similar to lines in 2 space, but there is a fourth option, and that's the second option here. So we can have parallel and distinct, and I'm actually going to show you that on our 3D graphing software here. Okay, so we can see here that our lines are parallel. They're unique lines, so they're not overlapping and they're never crossing. So that is going to be parallel distinct. And you've got a couple samples of what that might look like. So you'll notice that the direction vectors are the same, or they might be scalar multiples of one another. You can also have what we call skew lines, and this means that the lines, they're not parallel, but they just kind of miss each other in space. So this could be an example of an equation, 2 equations of skew lines. So I'll show you what that looks like in 3D. So you can kind of see here, no matter which way I I rotate here, you can kind of see that these lines are basically just missing each other in space, and even if they continue onward forever, they're really never going to touch each other. So there is an example of skew lines. And then we also have, they are not parallel and on the same plane. So what this is going to produce is essentially an intersection point. Okay, so you can see our 2 lines here and they're crossing over at the same point. You'll notice that the equations of these actually do share a common point, but that won't always be the case. So The equations don't necessarily tell you based on the point that you see here. We know we could have really any position vector out to these lines. And then finally, if you have two lines that are parallel and coincident, just like in 2D, if they're the same line, you'll notice that the direction vectors are the same or either scalar multiples of one another, and they'll literally be the exact same line. So that's our last example here. So you can kind of basically see that these lines are overlapping and they're basically just the same line. So this has infinite points of intersection. Okay, so for our steps for solving for intersections of lines in 3 space, the first thing that we always want to check is whether the direction vectors are parallel or not. So is one a scalar multiple of the other, or are they the same? If yes, you could have the infinite solution, so they're either parallel coincident, or you could have no solutions, meaning they're parallel distinct. So if they're parallel coincident, that means they share all points. So you're going to test a point from the first line to see if it's on the second line in both cases. And if you get a true statement, that means the point is on the line. If you get an untrue statement, that means the point is not on the line, and that will tell you whether they're parallel distinct or parallel coincident. If not, you're going to follow the next set of steps. So they could intersect once, or they could be skew, and that would mean they never intersect. So you're going to proceed to step 2. So we're going to do something very similar to what we did in 2D. Set up your parametric equations. This time you'll have 3 x, y, z for each line. You're going to set the equations equal to one another and simplify. And then what you're going to do is solve for both s and t using 2 of the equations only. The third equation is going to be used once we solved for s and t to essentially plug into the third unused equation to see if we get a true statement or an untrue statement. If you get an untrue statement, that means your lines are skew and there's no point of intersection. But if you get a true statement, this means that there is a point of intersection, and you can plug in your s or your t, or your s and your t, I should say, back into one of the lines to get that point of intersection. So let's take a look at an example. So like I said, the first thing that we're always going to check is my direction vector from line 1 equal to some scalar multiple of my second one here? So I think I can visibly just kind of take a look at this and decide. If k is equal to 2 here, then my first line is actually a scalar multiple of my second line. So this does fit that the lines are do have direction vectors that are scalar multiples. Therefore, I can say that the lines are parallel. Now, the other question here is if they are parallel coincident or parallel distinct. So sometimes it can be helpful just to kind of set up like 3 equations for x, y, and z. Let's say I'm going to test if the point 1, negative 9, 9 is on my first line. I could also test if the point 5, 11, 2 is on my second line. Your choice. So I'm just going to set up 3 parametric equations for my first line. And we're going to plug in the x, y, z of our point on our second line that we're trying to test. And we're going to solve for s and see if we get the s's all equal or not. And that will tell us whether our line is parallel coincident or parallel distinct. Okay, so I think we can see here that s is equal to negative 4. And then if we move the 11 over, we'll get negative 20. And that means s is negative 4 again. And the last one, we get, just making sure that I did this correctly. Okay, so we're getting 7 equals negative 2s. And when we divide that out, we actually get negative 7 over 2, or like negative 3.5. So this is going to tell me that these lines are not parallel coincident, meaning they have no points of intersection. So we would say, therefore, these lines are parallel distinct. And that means that there are no points of intersection. All right, let's take a look at another example. So the first thing that we are always going to check is if they are parallel or not. So is 2, 1, negative 3 equal to some scalar multiple of 1, 5, 5. I think pretty obviously here, if I take 2 and divide that by 2, I get 1. But if I take the rest of these and divide these by 2, I'm not going to be getting 5 for these. So we would say no on this parallel one. If you're really not sure, you can basically just set up 3 equations. So you could set up something like this. And you can solve for the k. If you get the k the same for all of those, then they're parallel. If you don't, then they're not. But I think a lot of times we can just decide this by visually looking at it and making a decision. So if they're not parallel, we are going to take each of our lines and we're going to set up parametric equations for each of these guys. Take a quick second to do that. Okay, and same thing for line 2. Okay, now we want to take each of these and we want to find where the x's are equal, y's are equal, and z's are equal. So I'm going to create 3 equations. So this will be step 3. And this will be my equation number 1. I'm going to set the x's equal to one another. And then I'll simplify. So I'm going to bring the constants to one side and I'm going to bring the variables to the other side. So this is what we get for our first equation. Second equation, do the same thing with the y's here. We'll simplify this out. Notice that I'm keeping the t's first and the s's second as well, just so that once I go to do elimination, I can actually line these up. Not super important, but just helpful. Okay, and then the last one. So we'll bring this guy over. And same thing with the s. Okay, so there's our 3 equations. I'm going to choose 2 of these. Now you can choose these strategically if you want. So I'm noticing that with equations 2 and 3, I have a 5t with each of these, which would mean that when I go to do elimination, I can simply eliminate those 2 without having to multiply my equations or anything like that. So I'm going to go forward here and I'm going to use elimination. I guess that's actually, was that my step 2 here? Yes, so step 3 is to actually solve. So let's go to step 3. So I'm going to use equations 2 and 3. So we're just going to kind of set them up on top of one another. Make sure that everything is in line. I have the constants on one side of the equal sign. I have the variables on the other, and I have the s's and t's lined up. So because I have 2 positive 5t's, I'm actually going to subtract these guys. So that's going to give me 12 and negative 4s, making s equal to negative 3. Okay, now you need to use equation 2 or equation 3 to solve for the remaining t value. I think equation 2 would probably be the easiest here. So we're going to sub this into equation 2 in order to solve for t. Okay, so we've got plus, and when we bring it over, we'll get minus 3, and that means that t is equal to negative 2. Now you won't always get really nice numbers like this, so keep in mind if you have fractions, that's totally okay as well. Okay, so now we're going to go to the next step, and that is, now that we have solved for s and t, we're going to plug s and t into the third unused equation. So in our case, the third unused equation is actually equation 1. That's the equation that we haven't used yet, and we need to see if we get a true statement. So here's step 4. So is 4 going to be equal to t minus 2 times our s? And I think that actually is going to give us a true statement. So if we get a true statement, this means that our lines are must be crossing at a point of intersection. So I can plug in my s and t into line number 1, or line number 2, and I should get the same point. So you can use both of them to check if you want, or if you're confident in your math, you can just use one of them. So I'm going to plug into line 1, and we'll find our coordinates. So x is equal to 7 plus 2s. Y equals 2 plus s, and z negative 6 minus 3 times s. All right, so we're getting 1, negative 1, and positive 3. So our point of intersection is going to be 1, negative 1, 3. And notice that I'm putting round brackets because this is actually a point, not a vector. So we're just wanting to make sure that we use proper notation there. Okay, the other scenario, once you check if these are not that, and you find that these are not parallel, you're gonna kind of find the same thing happens, except if the lines are skewed, then you'll get something over here like 4 equals 5, which we know is not a true statement. And that should tell you that the lines are skew at that point, and then you won't even, you won't even do this last step of plugging them in. All right, let's try another one here. So you're going to check to see if they're parallel. So is 1, 2, 3 equal to some scalar multiple of 2, negative 1, negative 1? So I'm already seeing here that if I want 1 to become 2, I need to multiply by 2, but that is not the multiple that I'm getting for the last 2. So I'm going to say no on this one. They're not parallel. And basically what that means is either they are skew lines or they have a point of intersection. So that's what we need to figure out. So we're going to go forward with step 2, and we're going to set up equations for both of our lines again. Okay, so set those up. Okay, and part of this step as well is to create 3 equations. So we're going to create equation number 1 by setting the x's equal to one another. And we'll just rearrange to simplify. We'll create equation number 2 by setting the y's equal to one another. And the third similarly with the z's. Okay, so now we've got 3 equations. Choose your equations strategically here. I could use, let's say maybe we'll use 2 and 3 here because I'm noticing I have a negative t in both of these. Okay, so we're going to have to subtract these 2 equations because our t's are both negative. And when we do that, we're getting negative 1 and positive s. So we get that s is equal to negative 1 here. I'm going to sub this back into one of our 2 equations that we just used. So you can choose equation 2 or equation 3. Let's sub s equals negative 1 into equation 3. And when we move that over, it's going to become negative 3. And that means that t is equal to 6 here. Okay, so final step, we're going to take these 2 guys and sub them into the final unused equation, which is equation 1 here. So sub s equals 1 and t equals 6 into equation 1. And it looks like we're getting 3 equals 13, which is of course not true. And basically what this is telling us is that these 2 lines do not intersect. So there's no solution. And this tells us that the lines are skew lines.